Okay, so now we are discussing the applications where we can perform the circular motion. Okay, so applications of the circular motion. Okay, and application of circular motion. Okay, fine. So in this portion, we'll be looking at how. Okay, we'll be looking at how the different in the different motion, how the circular motion concept is useful. Okay, so let's say if I have the vertical circular motion, the first case as the vertical circular motion. Okay, where I have a circle. Okay, let's say I have the circle. Okay, and we have to analyze it at two different points mainly, right? The first point is when your object will be right here. Okay, and the second point is when your object will be right here. Okay, let's imagine that you have a stone or rock that you taught with a string. Okay, and you are moving it in the circular path. Okay, like this, right? And let's say A is this is point A, and this is point B, right? Now, can you guys tell? Okay, so the tension in this scenario, tension provides a centripetal force to keep in mind. Okay, so tension provides the centripetal force, centripetal force. Okay, now can you guys tell me at which point in the in this circular motion the tension will be highest? Any reason for that, bro? By the way, we know that at point A, the weight is acting downward. Okay, the weight is acting downward, and the tension is acting upward. Okay, and since if the force is acting in the opposite direction, that produces a greater tension. Okay, if the force is acted in the direction of the tension, then it will reduce the tension. Okay, so this is something. Okay, and always keep in mind tension act away from the point of observation. Okay, so over here the rock or the stone is going to be your point of observation because you are drawing all the forces according to the rock. Okay, and due to that it is the center of the observation, and tension is always act again away from the center of observation, so it is that way. Okay, now if we try to write the Newton's second law, so we should write tension minus W is equals to the resultant force, or let's say MA, okay, or MV square over R instead of writing MA, okay. Okay, since MV square over R is a original formula, okay, and M R omega square is not the original formula, so that's why I'll be using this formula every time, okay, and then if I want omega, I will substitute that, okay. Now, so so at point A, tension will be maximum. Okay, this is what you guys said. At point A, tension will be maximum, right? Okay, and at point B, tension will be minimum. Okay, because the weight is acting in the direction of the tension, so it will be minimum, right? Okay. So, but if the tension will be minimum at that point, so can we figure out what would be the value of the tension at that point, point B, or what would be the minimum velocity for which the circular motion to occur, right? So for at point B, if we try to make the forces, so tension will act in this direction as well as the weight will also act in this direction. Okay. Okay. So writing the Newton's second law for this point will be tension plus weight gives me mv square over r. Okay. Now, if you want the circular motion to complete itself, so the tension should always be greater than zero. Okay, or whatever the force that provides the centripetal force should always be greater than zero. Okay, so if I substitute that in the equation, okay, so it will be tension is equals to mv square over r minus weight, okay, and then it should be greater than zero. So mv square over r minus w, which I can write as mg, okay, should be greater than zero, right? And if I just take mg to the other side and if I cancel the things out, mg, okay, so it gives me v square should be greater than gr, okay, or I can write this as v should be greater than gr, right? Which means if you want the circular motion to be complete itself from at point B as well, so your velocity should be greater than this velocity, right? Is that clear, guys?
Yes, yes.
Perfect. And you can also justify this by finding out the acceleration as well. Okay, let's try to do a question. Okay, or you can also use a work energy method over here, right? Like if okay, this is, by the way, this is something that we've used with a force analysis, using the force analysis. Okay, so this is a force method. Okay, okay. If I do the similar thing using the energy method, okay, copy and paste. Okay, it depends in the question which quantities are given. Okay, so according to that, um, you have to pick which method you have to use. Okay, so now this is the energy method. Okay, energy method. Okay, so let's say the radius of the rod is given for now. Okay, I'm not doing the force analysis anymore. Okay, let me just erase them. Erasing the tension. Okay, done. Yeah, yeah, either. Okay, fine. And now let's say the radius of the rod is um let's say 10 centimeter. Okay, for the sake of understanding. Okay, fine. And then let's say okay, at point A, we have given with a velocity of 4 meters per second, right? Okay, and I'm asking you to find out or justify. Okay, it's more like a word problem. Okay, not a derivation. Okay, so I'm asking you to justify the justify that the rock complete the circular motion. Okay, so what do you guys do? Any idea?
What what does the question mean?
The question means that we know that at point B, there is a possibility that the object may fall down, okay, or the object can continue in the circular motion. Yes, these are the two
Yes.
possibilities at point B, right? So I'm saying to justify that the object at point B is completing the circular motion, okay? And if it is not completing the circular motion, then you have to give the reason accordingly, okay? Clear, getting the concept?
Yes. Yes.
Yeah.
Do you guys have any idea how to solve it, or shall we try together?
I think we
It's
have to find which one is more, B or A.
Which one?
Which value is
Okay,
more
okay.
like.
Um,
I think what's this Ke at K or G
yes.
gravitational potential at B or something.
Okay, let's try together. Okay, let's try together. So basically, the point over here is that if at point B, if the acceleration is greater than 9.81, then it will perform circular motion, okay? Circular motion, okay? But
At A or
if,
B?
sorry,
At A or at
at B,
B?
at B, at B, at B. Because at A, it is like justified, or it is easy to complete the circular motion through point A, but difficult to move this, complete the circular motion from point B, right? Because at point B, there will be minimum tension, okay?
Mhm.
Okay. And so if at point B, if the acceleration of the particle of the rock is greater than 9.81, then it will complete the circular motion, okay? And if its acceleration at point B is lesser than 9.81, then it will go under the free fall motion. It will fall down. It won't complete the circular motion. Is that clear, guys?
Yes.
Yeah.
Fall motion. Okay. Now, Um, we have to use the energy method to work out. Okay, so we know that we're considering that no energy is being lost, or there isn't any resistive forces and all of those things. Okay, now we can say that um, total energy at A should be equal to total energy at B, right? This is what the law of conservation of energy says, right? Clear? Now, the total energy at A will be in the form of kinetic energy only, right? So, plus GPE will be 0, okay? And the total energy at B will be in the form of kinetic and potential, right? So, GPE plus KE, right? It could be possible that kinetic energy at max height would be 0, but if the kinetic energy would go to 0, then it is not possible to complete the circular motion, right? Through point B, right? So okay, let's solve. So at point A, do we need mass? No, we don't. Okay. At point A, the speed is half m nv squared, okay, is equals to at point B. Can you guys tell me which formula to use for GP?
MGH.
MGH. Okay, good. And which height should we take in MGH in H?
The radius.
Are you sure?
Radius
Uh
times 2, so
The
diameter.
diameter actually,
oh,
right? Very good.
yeah, yeah.
Okay.
Yes.
So m into 9.81 into 2 times the radius, which is 20 exponent
Mm.
negative 2 to convert it into um into this thing. Okay. And plus the kinetic energy, which we don't know. Okay. Or the velocity, which we don't know. Right. So this is this. Okay. Now we can cancel m out, right, by taking m common from both the sides. Okay. So we are left with, so 4 squared 16 divided by 2 gives me 8. Okay. Equals to 9.81 into point 0.2. 9, or I can take it to the other side, negative 9.81 into point 0.2. Okay. And then I have to times it by 2, and then I have to root the whole thing out. So that gives me the velocity at that point. Okay. Can you guys please tell me the velocity?
3.475.
Okay. So you are saying
3.48.
3.475. Okay. Come on, picking your,
3.48.
wait. Yep. 3.48. 3.48. Fine. Meters per second. Okay. So this is the velocity. Okay. Now, if we try to find out the acceleration using that velocity, so we know the formula as a is equals to, or a is equals to v square over r. Okay. And then v is 3.48 squared divided by um, 10 exponent negative 2. Okay. So what is the acceleration? And this is going to be the centripetal acceleration. Yes, guys, how much?
Getting 121.104.
121. Okay, fine. So the acceleration is 121 point something. Okay. Or we can take it 120. Okay. 120 meters per second square. Okay. So since this acceleration is larger than the circuit the 9.81, so the object will perform the circular motion. Okay. The centripetal acceleration is greater than the acceleration of free fall, so it perform, or it completes the circular motion. Okay, fine. Now, so it is
Uh,
done. Yes.
is there any other way to solve this sort of question? Like if with the like not using.
You can use kinematics thing. Okay, and if you want to use the um, kinematics. Okay, so you have the initial velocity, you have to find out the final velocity, and for that, the displacement of the particle is 20, right? You can use that. Okay, let me just take that thing down. Okay, so if you're using kinematics, so you will do 2as is equals to v square minus u square. Okay, and we are interested in okay, we have the initial velocity, we have the radius. We don't have the final velocity. Okay. Okay. We have to find out the final velocity. We can do that.
uh, at B at point B V0, no?
No, we have to figure out what would be the velocity at point B. Okay. And then we have to figure out, or we have to make the conclusion. Okay.
Uh,
Okay. So point one 99 this and divided by zero point 0.1. Okay, no other way. Okay, so I don't think so it can be solvable using kinematics. Hmm. Hmm. Just a minute, please. Okay, so I don't think so because we have one velocity only and we have the displacement, we don't have the acceleration. Okay, so we can use we can use kinematics. Okay,
Okay.
now so this is one type of application. Now the other type of application is basically the bank turns. Okay. Okay, so the first one is a vertical circular motion. Okay, the second is the bank turns. Bank turns. Okay. You may have noticed that um, when you uh, when you go through the highways or bridges and it turns at some point. Okay, so the road gets slightly slanted or slightly inclined at the turning. Maybe you have experienced that, maybe or maybe not. I don't know, but I think you should you. I don't know. I think you should um, or you would observe that. Okay. It is something like this, based. It is something like this. Okay. So in those type of scenarios, just ignore for now any components. Okay. And this thing. Okay. And this thing. Okay. Now, so in like if you're turning through a road where the vehicle passes with a very high speed, okay, so they make the road in such a way or they make the road at an angle from the horizontal, okay. And the reason for that is since when you take a turn, the friction between the tire and the road provides a centripetal force, okay, which is the friction actually that provides a centripetal force to your car, okay. Now, if you're taking turn at at high speed, okay, the friction between the road and the tire remains the same, right? It won't change because you're not changing the road, you're not changing the material of the tire, okay, and the friction depends on the friction depends on that thing, okay. So if you are turning the object mv squared over r, if you are turning the object with a very high speed, with a very v is very large when you are taking turn, okay, so for that you required greater force f, okay, to provide you the enough centripetal force to help you take turn, okay. But since this is constant and it is depending upon the road material and your tire, okay, so it will have the fixed value. You can figure out some other way, right? And this is the fixed value, right now. At a very high speed, um this friction won't be enough for your car to take the turn easily and it will go skidding, okay. So to avoid that thing, we make the we make the road slightly slant, okay, or slightly tilted, inclined, so that when the object take turn, so its weight, the component of the weight, as well as the component of the normal reaction force provides a centripetal force uh, to the car or to the object to help it complete its turn. Okay, guys, that clear?
Yeah.
Yes, the concept
Hmm.
is clear. Okay. Okay.
What are there'll be friction, right, as well? Like
Yes.
on so would that be like away from away from the center or
No,
towards
towards the
that?
center, always. because friction provides is providing the centripetal force, so it should be in the direction of the like center, or toward the direction of the center of the circle, right? Or toward the direction of the turning point. Okay, clear?
Okay.
Now, so if we consider the normal reaction force, the weight is acting downward, okay? And if we consider the normal reaction force, so the normal reaction force is acting in it is always perpendicular to the surface, so that's why it's acting that way, okay? And if you make the component, so the first component that is acting upward will be n cos theta, right? And this one will be n sin theta, okay? And if you want to, no, we can't. We're not making the components of the weight. Okay. Now let's try to equate the things. Okay. So n cos theta, n cos theta. Okay. N cos theta. Okay. Um, provides the centripetal force. Oh, sorry. N cos theta is basically balancing the weight. Okay. So this should be equal to that thing. Okay. And um, n sine theta should be equal to the FC, or the centripetal force. Okay, it's not good. Better way is to write mv square over I over r. Okay, and now you can make n the subject from both the equation and you can solve. Okay, cos theta and then sine theta is equals to mv square over r. Okay, sorry, it should be down there, and there should be n right here. Right. Now, if you equate the two things, so you will get, come on, a second, please. Oh. Okay, so if you equate the two things, so we have to equate W cos theta equals to mv square over sine theta times r. Okay, so W over cos theta is equals to mv square over sine theta r. Okay, and at W you can replace it with mg, and you can cancel the things out. Okay, and then sine theta over cos theta is equals to v square over gr. Okay, you can replace that with tan theta, so it will be tan theta is equals to v square over gr. Okay, right. So this is a concept of the bank turns, okay, where you can relate the angle with the velocity that you are taking the turn with, okay, or you can find out the velocity, which would be easy for the car to take turn, okay, if you are taking that angle, okay, right? But if you keep the angle very high and you're keeping the speed low, then it may fall down or slip down. Or if you are taking the angle very low and the speed very high, then it may end up skidding the car, okay. Now this is the second concept, okay. The third concept is the concept of the conical pendulum, but it's not that much tested in our syllabus, so I'm not going through it. I'm rather going towards the questions. Okay, let's try some of the questions. Okay, so I have my workbook right here. Okay. So by the way, this workbook contain the questions from question till 24 November 24. So when I compile this, I won't have the access for 2025, so it's not in there. Okay, so for that, I think you have to use your Google and online passwords. Okay, and I think there are available some new questions. Okay, now let's try them out. Let's try these questions. Okay, I can take. Okay, let me. I'm not going through with these two questions. Okay, let's go through. ये चलो ये कर लेते हैं. Now, select the pages. This is this and this, and that is easy. This is difficult, and okay. Copy and paste right here. Okay. Irfan, can you please read the question?
Which one?
The first one.
This number two.
Yes.
Okay. A large bowl is made from part of a hollow sphere. A small spherical ball is placed inside the bowl and is given a horizontal speed. The ball follows a horizontal circular path of constant radius as shown in figure 2.1. The forces acting on the ball are its weight W and normal reaction force R of the ball on the ball. Can you
Okay.
scroll down?
Yes.
Yeah. Normal reaction force R is at an angle theta to the horizontal. By resolving the reaction force R into two perpendicular components, show that the resultant force F acting on the ball is given by the expression W is equals to F tan theta.
Okay. So for that, you first have to resolve the reaction force R. Okay. And you can resolve it by making the two components, the first in this direction. Okay. And that would be which component? The cos or the sine?
Cos.
Very
Cos.
good. R cos theta, and that one should be sine then. R sine theta. Okay. Now you can equate the cos sine theta is balancing the weight, while the cos theta is unbalanced, so it will provide the centripetal force. Okay. So R sine theta is equal to the weight. Okay. While R cos theta equals to um it is unbalanced, not equal to anything, so it is just providing the centripetal force or the resultant force which you are saying as F. Okay. Now we can make R the subject from both of the cases and we can solve. Okay. So when you make R the subject and when you equate, so your equation will be W over sine theta is equals to F over cos theta. Okay. This is the equation, right? Now you can keep F that side and you can bring sine theta to the other side, sine theta divided by cos theta. And you guys know that the cos theta over sine theta is basically the tan theta. Okay. So we can replace with W is equals to F tan theta. Okay. Right. That's it. Okay. Now please move on. Yes, Irfan.
Yeah, okay. State the significance of force F for the motion of the ball in the bowl.
Okay. Since F.
It,
Mhm.
it keeps the ball in The circular motion.
Very good. It provides a circular motion. Okay, very good. So, or you can say it provides the centripetal force to the ball. Fine. Please move on.
The ball moves in circular path of radius 14 centimeter. For this radius, the angle is 28. Angle theta is 28. Calculate the speed of the ball.
Hmm. Which formula you use?
F equals mv squared by r, yeah?
F equals to mv square by r. Hey, but we don't have the angle in that formula. Like you have to relate a
Mhm.
formula that contains theta and r so that will be able to find out the speed, right?
Yeah.
Uh, we can't use the expression, right?
We actually have to use this expression which we just found out. Okay.
Oh, okay. We can use this one. I was
Yes.
thinking. Okay.
Because
So
yes. So
so
W is
yeah.
equals
W
to F tan theta. Okay. And we know that weight is basically mg, and we know that F is a centripetal force or resultant force providing the centripetal force or equivalent to the centripetal force. So I can replace this with mv square over r, and this is yes, what you were saying, Meghlad. And tan theta. Okay, now you can cancel the m and m out, and you can make v the subject. So g is 9.81, radius is going to be 14, so 14 exponent negative 2 divided by velocity is your okay, velocity is to be found. Okay, and theta is 28. Okay, and you have to find out the v.
For 2.58.
2.58. 2.58?
Yeah, no?
No, it should be different.
something like 1.6.
Yes, should be that value. Are you getting that?
No. I keep. Oh, I think we have to square root, yeah.
You have to root it.
Yeah. Yeah.
Okay. Okay. So you should get 1.6.
1.6.
Very good. Okay, let's move on. Can you please read the question with that?
With reference to velocity and acceleration, describe uniform circular motion.
Okay, so in uniform circular motion, I think we didn't include the definition of uniform circular motion. Um, nope. Okay, I should have to, but just write it right here. Okay, so uniform circular motion is defined as it is defined as uh, the motion in which acceleration and velocity are perpendicular to each other, okay, and acceleration is directed toward the center. Okay, please move on.
Two cars are moving around the horizontal circular track with one car follows path X and the other follows path Y as shown in Fig 1.1.
Okay,
So,
so Okay, let's move on.
The radius of path X is 380 meters per path Y is parallel to and 27 meter outside path X. Both cars have mass 790 kg. The maximum lateral friction force F that the cars can experience without sliding is the same for both cars.
Okay. Okay.
The
So
maximum speed.
wait, wait, wait. This is something very important. Okay. The maximum lateral sideways friction. So this friction is basically the only force providing you the centripetal force. Okay. And they're saying the centripetal force for both the cars are same, right? While their circular track are different, right? Their radiuses are different, right? Okay. Now please move on.
The maximum speed at which the car on path X can move around the track without sliding is 94 meter, meters per second.
Okay.
The
Which
track.
formula we use?
So can you go up a bit? So
Okay, it's just a simple concept. You can just use F is equals to
well,
mv square over r.
okay.
Okay, mv square over r. Okay, so the force F is okay. So the mass is given both the car having the same mass 790. Okay, and the velocity is 94
Oh.
divided by for the car X it is 318. 318. Okay, how much?
21951.
21951. 21, sorry, 21951. So you can write this as 2200, triple zero. Okay, please move on. Yes, yes, Migdad,
Yes,
where
sir.
are you?
Uh,
Okay, please move on.
always. Both cars move around the track. Each car has the maximum speed at which it can move without sliding. Complete table 1.1 by placing one tick in each row to indicate how the quantity indicated for the car on path Y compared with the car on path X.
100. Okay, so they're saying the centripetal force. Okay, so since they have told you that the forces are the same for both of the cars, right? So this means the centripetal force is going to be the same, right? Yes.
Right.
Okay. And then if we use this concept, okay, so the centripetal force should be the same. Okay. If we use the concept of the maximum or use a formula, so
Okay.
F is equals to mv square over r. Okay. And to find out the maximum speed for car Y. Okay. Because we have the maximum speed for car X. Okay. Since they're saying the forces are same, so 2195 and something. 5 1. Okay, so this will be the force for y as well. Okay, but its radius is 318 plus 27, 318 plus 27, because its radius is its path is greater than okay, greater than the paths for x. Okay, and divided by the mass is going to be 791, 790, 790. Okay, and you can divide that by you can root it, so you'll get the velocity. Okay, what is the velocity?
Sir,
बोलिए. Yes.
This first row, it's centripetal acceleration, not force.
Okay. So, okay. Sorry,
Would
sorry.
it still be the same?
Um, if the centripetal acceleration, if the centripetal force is the
Depends
same,
on
so the
the
centripetal
mass, no?
acceleration will also be the same.
Does
Yes,
it depend
sorry.
on the
Bro, both
mm,
the car has the same
no?
mass, okay? They've
Ah,
mentioned
okay.
that, okay?
Okay, then yeah, it's the
Okay.
same.
The centripetal force depends upon the centripetal acceleration, okay? So if the forces are same, so the acceleration remains the same, okay? And using that, we can find out the velocity and how much?
98, I think. 98 after
98.
rounding.
Okay.
Yes.
So it is greater than that, okay? So the time taken for one track, okay? So you can find out the time taken, you have to find out the omega basically. So basically you can use V is equals to R omega, okay? And you can expand R by keeping its value to pi over t, okay?
Bye bye T.
Very good. And then just make t the subject, okay? And R is 318 times plus 27 plus 27, okay, and times it by 2 pi divided by 94, okay. So by the way, if you have
98.
98, yes, just find that out. This is for y, okay.
22.1.
22.1. Can
Yeah.
you do the similar 22.1? Can you do the similar working for x? But you have to consider this as 318 only, and you have to take 98 as 94.
21 point,
20,
21.3.
21.
21.
Okay. So this mean it is also greater, right?
Yes.
Clear? Okay. Okay. Irfan, can you please read this question?
State what is meant by centripetal acceleration.
Yes. So centripetal acceleration is basically
The rate of
uh,
change of
mhm,
angular speed.
uh actually no, the rate of change of velocity. But you have to. It's we rather say that uh, it is the acceleration. Centripetal acceleration is the acceleration perpendicular
To the
to
velocity.
velocity. Okay. And it is always directed toward the center, but since they're asking for 1 mark, so then it's fine. Okay, let's move on.
An unpowered toy car moves freely along a smooth track that is initially horizontal. The track contains a vertical circular loop around which the car travels, as shown in figure 1.1. The mass of the car is 230 grams and the diameter of the loop is 62 centimeters. Assume that the resistive force acting on the car are negligible. State what happens to the magnitude of the centripetal acceleration of the car as it moves around the loop from x to y.
Okay. So by the way, they're saying it is an unpowered car. Okay. So unpowered car mean no engine, nothing. Okay. And mass is given, the diameter is given. Okay. So by the way, which force in this scenario provides the centripetal force? Because that decides the centripetal acceleration. Okay. So what do you think?
The You mean at point x and at y, or
Yes, both at both the point or throughout the circle, which force will be responsible for the circular motion?
uh Normal reaction force.
Very good. The normal reaction force or the contact force. Okay. So for X and Y, we have the contact force, but as it move up, the contact force, the grip between the track and the car or the toy car loses as it go up. Okay. So the contact force decreases. Okay. So the centripetal acceleration will also decrease. Okay. Clear?
Yes.
Yeah.
Okay. Should be E. Okay. Please move on.
Explain if the car remains in contact with the track, centripetal acceleration of the car at point Y must be greater than 9.8 meter per second squared.
Yes. Okay. This is the same thing. Okay. And you can say that why the centripetal force at the car at point one. Okay. Um, the 9.81 acceleration is due to weight, okay, which causes the free fall motion, causes the free fall motion, okay, and the
It's a
then
weak motion can over come the acceleration, yeah, of
yes,
9.8.
like there should be more force to overcome this 9.81 acceleration, okay.
Yes.
So the centripetal H
Accelerate.
okay, the centripetal free fall motion. Okay, so the centripetal force or the centripetal acceleration, sorry, centripetal acceleration required uh the force greater than weight. Okay, so yes. Now please move on.
The initial speed at which the car in B moves along the track is 3.8 meter per second. Determine whether the car is in contact with the track at point Y, show your workings. So
Okay,
this is basically the same as
what we
the
have done,
last one.
right?
Yeah, yeah.
Okay, so they have given us the initial velocity. Okay, we can use the law of conservation of energy. So total energy at x should be equal to total energy at y. Okay, and at x there will only be kinetic energy half mv squared, and at x there will be mgh plus half mv squared. Okay, m goes off, and then 1 over 2, and then velocity is going to be 3.8 squared, and then negative 9.81 into h is 62, 0.62. Okay, this is h, which is the diameter given in the previous part. Okay, and then times it by 2, and then root the whole thing. So you will get the velocity.
1.51.
1.51. Okay, now just put it in the acceleration formula, v square over r. Okay, so 1.51 is squared divided by the we have to use the radius, so that is 31, so 0.31. Okay,
7.34.
7.34. So acceleration is 7.34. So since you have to give the conclusion, since this acceleration is less than 9.81, so it will fall down. Okay, let's move on.
So just with the reason but without calculation, whether your conclusion C would be different for a car of mass 460 gram moving at the same initial speed. What is the mass of the
In half the value, 230.
okay. Mm, it will without calculation
Look, look, look,
But
look.
then fall down faster, yeah.
it will fall down more, yeah.
No,
Fast.
bro, the mass is cancelled out. Okay. So there isn't any effect of the mass on the motion, on this motion, where we are not considering any friction force or something, right? Clear? If we consider the
Yeah.
friction or the other things, then the mass will be considered, okay? So you can
Okay.
say that um, the the system the system is, or the equation is independent dependent of mass. So the uh okay, so unchanged. Okay. And the last question, yes. Okay, last question. Can you please read with that?
Wait, it's a bit laggy.
Mm-hmm.
Just a
Okay.
steel sphere of mass 0.29 kg is sus sus suspended in equ- equilibrium
Equilibrium.
from a vertical spring. The center of the sphere is 8.5 centimeters from the top of this of this of the spring as shown in figure 2.1. The sphere is now set in motion so that it is moving in a horizontal circle at constant speed, as shown in figure 2.2.
Okay. Constant speed, fine. Move on.
Distance from the center of the sphere to the top of this spring is now 10.8. Explain with reference to the forces acting on the sphere why the length of the spring in 2.2 is greater than 2.1.
Yes.
So we use F equals kx, yeah?
No, they are asking. So basically, previously there was 8.5 centimeter of length, and over here this 10.8, right? So there's an extension, and extension in the spring happens when you have the tension. Okay. So as you're moving, so the horizontal component, if you make the two components, okay, so one component would be upward, okay, the other component would be downward, would be this horizontal, okay, and this is the weight, okay. So basically, the horizontal component is basically unbalanced that produces the tension in the wire and the tension in the spring, which cause the spring to extend, okay.
Yes.
So we can say that the force okay, the force on the force due to the spring, the force due to the spring, which is tension, okay, spring um provides the centripetal centripetal acceleration, or you can rather add the word horizontal, horizontal component of the force due to the spring tension provides the centripetal force, while the um, vertical force balances the string, balances the weight of the bob. Okay. Acha ji. So due to that tension, due to that horizontal component of tension, um, there will be there will be extension, or there is extension. Okay. Now please move on.
The angle between the linear axis of this of this plane and the vertical is 27 degrees. Show that the radius r of the circle is 4.9.
Okay. So we have given the okay. So this 27 is basically right here. Okay, 27. Okay, and if you apply the trigonometry, so you will find that out. Okay, so sine theta, okay, is equals to r over hypotenuse, which is 10.8 centimeter. Okay, and 10.8 sine 27. Okay, how much?
4.9.
4.9. Okay, so okay, now please move on.
Show that the tension in this spring is 3.9,
Okay,
3.2.
so do we have the angle, we have okay, we can equate it with the weight if we have the weight or mass. Okay, we have the mass. Okay, so we can say that the weight is basically equal to T, which were what was the component? T cos theta. Okay, so weight is basically pretty equivalent to T cos theta, right? Getting that?
Yes.
And
Yeah.
weight is mg, and over cos theta is going to be, so this is going to be your T. Okay, now please put in the value and solve.
What's M?
So m was 2.29 into 9.81 divided by cos theta is 27,
Yes, 3.2.
3.2.
3.2. So now you have the tension. Okay. Now they're saying the spring constant. To find the spring constant, you know that the force F is equals to kx for the spring constant. Okay. And over here, tension is basically the force. So 3.2, and extension is going to be 10.8
10.8.
minus
Minus
8.5, right? And since they're asking in centimeters, so you can keep it in centimeters.
1.4.
9.4,
No, 1.
1.4. It should be 0.14.
I'm getting
1.
1.4.
Okay.
Yeah.
Huh, 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 huh. Wait, I have the tension. Okay. And no, wait. The tension in the spring's constant. Mm, fine. We have 3.2 force acting vertically upward, or in this direction. Okay. And the downward force is in this direction. Okay. This is the force and this is the force. And when you subtract them, the extension is correct. The formula is also correct, but the answer is not correct. It should be 0.15, but let's see how. Okay, so the tension in the wire is this much. If we take 3.2, so it is basically balanced with the other force. Come on. We have to consider the force on the spring. The spring obeys the Hooke's law. The tension in the spring is this. Okay. So force is 3.2, which is in the spring, the tension, okay, divided by, should be considered the weight. And if we are considering the weight, so we are not allowed to subtract the weight directly. Okay. The answer they've wrote in the marking key is 0.15, but it is not making sense. The net force produces that, right? So the change in the force produces a tension. Okay, so it should be 3.2 cos 27. Okay, and then divided by 10.8 minus 8.5, 1.32. Nope. Okay, just skip it for now. Okay, because just skip it for now. Let's move on. I'll explain it on. In B, to determine the centripetal acceleration. Okay, so for centripetal acceleration, which formula you can use? We have the force and we have the angle. Do we have the velocity? We don't have it. Fine. So, so acceleration is equals to, if we use v square over r, no, we can't use that because we have the radius, but we don't have the velocity. Okay. Any other formula? If we use, okay, if we use t sine theta in it as like t sine theta, which is the centripetal force, is equals to m r omega square or mv square over r. Okay. Or we can just write this thing. Okay, so 3.2 sine theta or sine 27 divided by the mass is 0.29. Okay. So can you tell me the acceleration?
Five.
5.
Yes, five.
Okay. And okay. The period of the circular motion. Okay. So for the period, you can do omega is equals to 2 pi f, 2 pi
2
over
pi by
t,
t.
right? But we don't have omega. We have to find out for the omega
Um,
first. Mm-hmm.
we can do A is equals to R R
A,
omega
yes. Okay. So
A is equals to 2 pi over t the whole square.
5, okay. 5 divided by r is 4.7. Exponent negative 2 and whole thing under root gives me the omega. And then I can make um 2 pi over t the subject and 5 over, like whatever you'll get the answer, just make the t the subject
10.3.
and put the answer right here and you'll get the final value. How much?
10.3 or omega. Omega only.
Okay.
I'm getting 0.6.
Okay. Perfect. Right. So now
Yes.
that's it. I am ending the class. Okay. So first chapter is done. I'll be sending you the question. Okay, I'll be
Okay.
sending you the questions, okay, and you have to complete the remaining question of the circular motion, okay, and then in the next week we'll try to start the other chapter, okay.
Okay.
Okay, take care, guys. Enough is.
Yeah.